Hi guys, my name is Sarah Rochniak, and I'd like to take a few minutes of your time today to talk about something that I think is pretty exciting. How many of you ever played with Play-Doh as a kid? I know I love the stuff. I like to make mermaids and castles with my brother and sister. As a child, I thought it was amazing being able to sculpt whatever shape I could possibly imagine. What would it mean if we as a civilization could sculpt working models of whatever we needed, effectively, quickly, and most importantly, at a low cost? I'd like to start this off by sharing two facts. The first, what is 3D printing? Now, I'm sure most of you have heard of or even seen this new technology in action. It's all the buzz in the world of technology today. Well, 3D printing is a process by which a physical object is made from a three-dimensional digital model. This is done by layering many thin layers of material on top of each other until the object is born. The second thing I'd like to share with you today is this. An average of 21 people die each day waiting for transplants that can't take place because of the shortage of organs available for donation. The rest of this presentation will be dedicated to telling you what these two seemingly random facts have in common. First, a history lesson. How did this all start? Well, 3D printing technology first appeared as early as the 1980s. It was first used as a way to create quick and cost-effective prototypes, like the engine you see here. In the mid-1990s, the field started to diversify into the two distinct groups that we still see today. The first revolved around 3D printers that kept the focus on improving concept development and functional prototyping. These were developed specifically as office and user-friendly, but most importantly, cost-effective systems, in the same vein as the precursors to the desktops that we all use today. Now, the second group was geared toward the high end of 3D printing, which is still very expensive. These systems produce high-value, highly engineered, and complex parts. The development of this technology is still ongoing and growing, but the results are only now really starting to become visible in production applications across the aerospace, automotive, and medical fields. Some more history, but this time about organs. The first human organ transplant was a kidney transplant performed in 1954 by Dr. Joseph Murray, who went on to win the Nobel Prize for his work. The first heart transplant was performed 13 years later in 1967 by Dr. Christian Barnard. Now, the donor of the first kidney was the identical twin of the recipient, and therefore there was no risk of immune rejection of the organ. The recipient lived for 8 years following the transplant. In contrast, the recipient of the first heart transplant lived only 18 days. That's a bummer. But he didn't die because the new heart failed. He died because of the pneumonia he contracted due to his weakened immune system being compromised by the anti-rejection drugs. Here lies one of the biggest problems with organ donation. The attempt of your body to reject that invading mass of tissue. It's never seen it before. What's it doing here? What would you guys do if someone came up to you on the street and shoved a needle in your arm? I don't know about you guys, but I would get that needle the heck out of my arm. Even if it was what was keeping my body alive. I didn't know that at the time. The same concept applies to a new organ. So despite these side effects and costs, organ transplants have become common enough that the shortage of donors is now the key constraint. As of 2011, there were over 100,000 Americans waiting for a donor organ. And as I said before, of those waiting, approximately 21 die each day. It's pretty crappy. But don't get too down. Medicine, ever evolving, is starting to make headway. In 2011, a milestone was reached as medicine attempted to circumvent the problem of rejection with the world's first transplant of a regenerated airway using a synthetic scaffold. What a bunch of fancy words. What that means is an airway was grown in a lab for this patient from her own cells. And because of this, the patient getting the transplant did not need to take the anti-rejection drugs. And because the scaffolds were made in a laboratory, the patient did not have to wait for a suitable donor organ to become available. It's through breakthroughs like this that open the possibility that the waiting list for organ transplants could be reduced or even eliminated. What would it mean if we could print our own organs? Well, as I said before, 3D printing would be grown from your own cells. Therefore, no chance of rejection. 3D printing would allow for the design of the needed organ through highly precise cell placement and high digital control of speed, resolution, cell concentration, drop volume, and even the diameter. Organs could quite literally be printed to your own size and specifications, tailored to a perfect fit. Patients would no longer wait for years, hoping for someone else to die so that they could live. At this point, you might be thinking, what's the problem? Let's get to it. However, as with most things in life, it's not that easy. 3D bioprinting is very complex. So far, scientists have successfully engineered 3 categories of organs: flat structures such as the skin, tubular structures such as urine tubes and blood vessels, and hollow structures such as the bladder. Now, to name just a few of the components involved in making any of these structures, there's the choice of materials. The actual cell types. For example, the heart has multiple types of cells that perform different tasks and are all essential to proper function. They must be arranged in the proper order and to the right depth. Not to mention the technological challenges faced relating to the sensitivities of working with living cells and the actual construction of the different tissues. They must be provided with a system to facilitate oxygen gas exchange. They must constantly be surrounded by the appropriate nutrients and growth factors, and they must have a waste product removal system, otherwise they will die before they ever reach your body. The most complex organs, of course, are solid structures such as the kidney, liver, and heart. Some of the challenges we face with these organs are learning to grow the billions of cells required for them to survive, as well as learning how to best supply the new organs with oxygen until they are integrated into the body. Here you see a beating heart. This structure, in all its complexity, is aptly at the heart of life. Its function, something that most of us rarely even observe on a conscious level, beyond, say, feeling our heartbeat, is at the base for all of our bodily functions, whether it be delivering oxygen to your brain so that you can think, or move your hand to wave to a friend, or acting as the carrier system for important nutrients needed throughout the body. Us animals could not survive without it. Creating a working, beating heart to transplant into patients would be the crown jewel of regenerative medicine. How far off are we? Well, according to Dr. Anthony Atala, one of the leading experts in the field, when asked about the timeline, he said, "Science is unpredictable, so it's impossible to say for sure. But I think we can safely say that the time frame required to routinely print and implant complex organs is decades rather than years." While we may still be a long way off, everyday advances are being made to bring us closer to this goal. There are many cutting-edge and very interesting projects with different applications that are contributing to this. What are these other applications? How could the 3D printing of organs advance science beyond just organ donation? A new project has come to fruition that I personally think is very cool. This project is called Body on a Chip. Here you can see the layout for each of your major organ systems in a schematic. The aim is to print your entire organ system onto a 2-inch chip, all connected by a blood source, just as it is in your body. This would enable companies to perform better drug testing. The 2-inch body on a chip would represent a realistic blueprint of all our major organ systems, with a mini heart, liver, lungs, even brain. This could create a testing ground for understanding how the body might react to dangerous diseases, chemical warfare agents, and even new drugs developed intended to defend against those biological or chemical attacks. Technology like this could replace animal testing as we know it, as well as save billions of dollars on dead-end drugs that fail once they get to human trials. Other applications of 3D printing in the medical field include customized implants and prosthesis. These prostheses are truly a cut above what we can produce now. Formed from a digital model of your leg and built layer by layer to your exact shape and dimensions, they offer more comfort and stability than what is available by even the most high-tech of machines. Individual and customized anatomical models for surgical preparation. Here you see a neurosurgeon practicing on an exact replica of a girl's brain. He's able to run through the entire surgery, start to finish, knowing where the structures of her brain lie, how thick or thin they are, and most importantly, can do so without the risk of harming the patient. Scientists are even studying printed cancer cells that mimic the behavior, size, and shape of tumors, observing and testing new drugs on them. Compared with traditional 2D cell structures, the additional dimensions of a 3D culture better reveals the tumor cell's characteristics. 3D printing is the future of many fields. Its applications will be seen across our communities for years to come, particularly in medicine. I hope that you're all as excited as I am about the possibilities that future holds. Thank you.